Hello guys and welcome back. This is part 2 about how to make a bloodline or a family of tipplers or a family of rollers, family of racing homers. Before going to the details of part 2, I want to just show you. We start from where ended in part 1. I did not do the third generation. I'm just doing it real quick here to show you guys that each one of the third generation, the F3, will have the same set of the genes. So I put male 1, female 1. We put male 2, female 2, just to make it easy for everyone. And the male 1 is from grandson 1 on the daughter from the second pair. Same thing here. The daughter from the first pair with the son from the second pair. So it's a straightforward method, but it proves every time they will have the same set of genes. So this is male 1, and this is what we ended up with. 50% from father, 50% of mother, and this is the set for male 1 or female 1, because they come from the same, they will be sister and brother. Male 2 or female 2, the same thing. So from math point of view, this method is proved to give you the same set of genes for every generation, and that's why it says distribute the genes equally. That's part 1. This is one of the things. The second one that we would like to talk about, I would like to talk about today, is if someone look deeply at this method and focus on the genes, what kind of a tippler or a roller or anything, if you apply this method, what kind of family that has 4 different set of genes? Because we started with 2 pairs, and we see all the genes from this basic foundation pairs are being transferred separate through the next generation and forever. Is that what we want? Is that what I want? If those young babies every year will have 4 different genes, is that the family I need? The answer is no. Before that, let me give you a quick example here, and we will come back to the gene part. This is an example that I use most of the time when I teach my kids math. Some people don't like math. Some people like me are addicted to math. Anyway, so when I teach my kids, when I explain mathematics problems, solutions to them, I tell them always, a 5 times 3 is 15. You can do it. You add the 3 to itself 5 times, or you add the 5 to itself 3 times. Which one is faster? Which one is better? They will say 3 times is better than 5 times, because we will get 15 in both cases. Now let's go back to the method. The article here tells everyone this method, explain it, and it shows the genes will be distributed equally, but it does not put restrictions about what kind of pairs you will be using. We can use male A and male C to be brothers. So instead of having A and C, we will have A and A, because they have the same set of genes, almost. We can use, so that reduces the amount of genes in the next generations from 4 sets of genes to 3 sets of genes, which is better. Instead of having C, we will have 50% of A, 25% of B, and 25% of D. Is that good? I think so. Instead of using a female B and a female D, two different females. We can use female B and female B also. Like, sisters or half sisters, they will have very similar genes. So here we will, instead of having offsprings next generation with 4 sets of genes, we will have them with 50% of A and 50% of B. So it's all about us. It's all about us, how to pick those basic foundation pairs. Another example to make it acceptable for everyone, understandable for everyone, I need to mix, for example, just making examples here. I'm talking about tipplers, and all my examples will be about tipplers. So I will pick the males to be Harry Shannons, for example, and I will pick the females to be Pilot or Bowdens. So that eliminates the too many sets of genes to only 2. Set of genes that comes from the males, the Shannon, and they are very related. That's how I pick them. And set of genes that comes from the females that are very similar to each other. So instead of having 4 sets of genes in every generation, I will have 2 sets of genes. 50% of A, almost, or 50% of B. It's approximate, not exact number. We have to understand that. It's about probability, okay? So it depends on me as a breeder how to make them look alike, how to make them look different. If you take a look now at the Harry Shannons, they all look alike around the world. If you take a look at the Pilot tipplers, they all similar. The Bowdens, they all similar. Gordon Hughes, they all similar. Sheffield, they are similar. So when I make my family of tipplers, it depends on me as a breeder how to pick those. Let's go outside, put some examples, and let us see the good example and the bad example. So this is an example that has so many genes. So we will assume that's the male A, that's the female B, and that's the Shannon tippler. That's the male C, and that's the female D. What we have here is a combination of 4 different families of tipplers, as you can see. This one, that's different. She is different, and he is different. They all look nice, but that's a bad combination. Let's switch to a better combination. Now what we have, we should have a better combination now, because 2 are from the same family. So we reduced the set of genes from 4 to 3. This guy has a set of genes. This one here has a set of genes, and the ones in the middle has a similar set of genes. Can we make it even better? I think so. Let's do something even better. And this is 2 sets of genes. That's a pair, A and B, and that's a pair, C and D. A and C, set of genes, B and D, another set of genes. So it all depends on you how to manage it, and the key is your brain. The theory is correct. It all depends on the application. Breeding and genes, genetics are is applied science. So it depends on the one that applies it. Hope you like part 2, guys. Thank you so much for watching, and have a wonderful breeding season.